How good is it? Let's talk about the performance of a predictive model, how well it predicts, and how we measure and report on its performance. Let's start with the decision tree to predict mortgage churn that we've been discussing. Without any additional information, you can tell just by looking at this, the decision tree provides value. Why? Because of how the probabilities differ across the leaves, the endpoints of which there are 10, each one signifying a segment of customers. The probability of churn for those segments ranges from 2.6% up to 40%. This means the tree succeeds in differentiating between groups of customers that are relatively much more or much less likely to defect. The ability to distinguish between dramatically different risk groups is the name of the game. It's what the modeling process sets out to do so that the groups can each be treated or handled accordingly. But how do you measure the overall performance of the model? There are various things you can measure, including accuracy, profit, lift, and a number of other options. So I'm now going to tell you why accuracy is usually the wrong metric and why lift is usually a useful metric. So as I mentioned in the previous video, in the mortgage data from Chase Bank, the overall churn rate was about 12%. This means that within a limited number of months, 12% of mortgage customers will defect. Since 88% won't defect, if I predict that no customer will ever defect, always predict no, 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 I achieve an accuracy of 88%. That's the smartest dumb model I ever heard of. I think I just broke some kind of world record. Accuracy often sounds like a natural place to start, but if you think about what it actually means, it's just this: accuracy, the proportion of cases the model predicts correctly. How often are you right? What proportion of the time is the prediction correct? For what percentage of cases do the model's predictions turn out to be true? All different ways to say what accuracy is. So, when the ratio of positive to negative cases is unbalanced, skewed away from an even 50-50, it's trivially simple to achieve a high accuracy. So if someone produces a complex model and brags about it having high accuracy, that alone tells us nothing about how much value it provides in comparison to a ludicrously brain-damaged, insipid model that just always predicts no, 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 no. And this ratio is usually unbalanced. You want it unbalanced. When the thing you're trying to predict is more rare, there's more value to predicting it. For example, direct mail might only get a 0.1% response rate, or even less. So correctly predicting each of those rare responders is so valuable. But predicting accurately who will respond is easy. Just always say no, and you get a 99.9% accuracy. You're amazing. Same exact thing with detecting which transactions are fraudulent. It's a good thing that only a very slim fraction of fraud are fraudulent, and the overwhelming majority of transactions are legitimate. So in this churn modeling example, the model was actually built on data only for customers with relatively new mortgages between 1 and 4 years that have terms of at least 15 years in length. So customers defect more than average, since borrowers who've been paying off for their mortgage for more than 4 years are more likely to stick with their mortgage as is. However, it's still 12%, far below an even 50-50 split between positive and negative cases, defectors and non-defectors. The full population would have an even lower proportion of positive cases. Lift, on the other hand, is usually a much more meaningful, revealing way to measure the performance of a predictive model. Remember this skunk example? We showed how direct marketing's profit multiplied by finding a segment with a lift of 3, that is, a group of customers 3 times as likely as average to respond to marketing contact. The arithmetic we covered showed how that lift translates into a profit multiplying by a factor of 5. Well, in this churn modeling example, consider the segment on the far right. It defines a group of customers with a 40% churn rate. That's 3.3 times the average. So that segment has a lift of 3.3. We can say this model achieves a lift of 3.3 for that segment. This means that if we invest in resources and/or discounts to retain customers in that segment, our efforts will be 3.3 times as effective as if we invested the same into a random segment that had the baseline 12% defection rate, since targeting that segment means we successfully contact 3.3 times as many would-be defectors. So let's formally define lift. Lift, a multiplier, how many times more often the positive class occurs within a certain segment defined by a predictive model in comparison with the frequency of positive cases in general. We say that a predictive model achieves a certain lift for a given segment. To conclude, accuracy is generally not a useful measure of a predictive model's performance, but lift usually is. Lift directly informs the improvement a predictive model can achieve for business objectives like increasing profit and decreasing customer churn. Of the various performance measures that come into play, lift is relatively easy to understand and is certainly widely known and frequently employed. So it's well worth the time to become comfortable and fluent with the concept of lift and how to calculate and work with it. So we'll revisit lift, practicing various ways to work with it throughout the courses of this specialization.